record this class. So class now is being recorded. And we have a couple of people to present. And Yingping, okay, let me make a presenters. All right, anyone can start if you're ready.
I'm presenting 4.7. Suppose that a die is rolled twice. What are the possible values that the following random variables can take on? A, the maximum value to appear. Oh,
It's gone, the screen sharing is gone.
the maximum value to appear in the two rows. So A and B have the same values, which is 1, 2, 3, 4, 5, and 6. In the case that if both dice land on, for instance, first dice on 1 and then the second dice on 1, then 1 is the maximum and the minimum. And the same thing goes for 2, 3, 4, 5, 6. And then C, the sum of the two rows, is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Since if the possibility that the first dice lands on 1 and the second dice lands on 1, then the sum of two dice, which is 1 plus 1, is 2. And the same goes for first dice on 1, second dice on 2, which is 1 plus 2, which is 3, and so on to get to 6 and 6, which is 12. D, the value of the first row minus the value of the second. That is -5, -4, -3, all the way to 5. In the case that if the first row lands on 1 and the second lands on 6, then 1 minus 6 is -5. And if the first row lands on 1, second one lands on 5, then 1 minus 5 is -4, and so on until you get first row 6, second row 1, 6 minus 1 is 5.
Great. Yeah. Yes. Nice. Nice. Thank you. Okay. Okay, great. You guys are talking about which ones to pick. Okay, who is ready next?
I got question 4.74. Considering a rotate wheel consisting of 38 numbers, 1 through 36, 0 and 00, if Smith always bets that the outcome will be one of the numbers 1 through 12, what is the probability that A, he will lose his first 5 bets? The outcome for the wins is 12 over 38. Then the lose is 1 minus the win, it's 26 out of 38. The first 5 bet going to lose, it's 26 over 38 times 5 times, so it's to the 5th power is 0.15. Then B, his first win will occur from his 4th bet, so first 3 will be lose and the 4th one will be win, so it's 26 over 38 to the power of 3, it's times 3 times, and then times 12 over 38. It's 0.1012.
So this is question 74. My goodness.
Yep.
Okay, great. All right, anyone has any question? Good job, Hao.
Can you see my screen?
Yeah.
Okay, that's 4.10. Let X be the winning of a gambler. The P of I equal to probability of X equal to I. And suppose that P of 0 equal to 1/3. P of 1 equal to P of -1 equal to 13/55. P of 2 equal to P of -2 equal to 1/11. P of 3 equal to P of -3 equal to 1/165. And compute the conditional probability that the gambler wins when I equal to 1, 2, and 3, given that he wins a positive amount. So we have probability of the P of 1 given W. W implies the positive wins. And the 1 implies when I is 1. So we have when I is 1, 2, and 3. So since we know all those are independent probability for each event, so when they add up, they have 1. For the positive amount, we just add P of 1, P of 2, and P of 3. So we got 1/3. And then we just plug in the value. We have P, when the I is 1, we have P1 intercept W. So we have those 3, and then among those 3 we choose P1, so that would just be P1, and that would be 13/55 divided by the probability of W would be 1/3. We have 39/55, and similarly for rest of them, we got those 3 answers.
Nice. Nice. Anyone has any questions? Yeah, I even like your notation. Probability of 1. That makes sense. Okay, thank you, Jie.
Thank you.
Who's next?
Hi, Professor.
Yeah, Catherine.
You can hear me?
Yes.
Okay. So I'm presenting number 1 of chapter 4.
Okay.
So Sophie. Okay. Sophie is choosing 2 coins randomly from a box containing 4 $2, 5 $1, 8 50-cent, and 3 20-cent coins. Let X denote Sophie's income. What are the possible values of X, and what are the probabilities associated with each value? So in here, I made a box in here, and $2, $1, and 50 cents and 20 cents. And since from all these coins, we know that there's total of 20 coins, and we need to choose randomly 2 coins. So it'll be like 20 choose 2 ways to choose, which is 190 ways to choose. And the possible outcomes of choosing 2 coins from a box is there's $2 and $2, which is 2 and 2, and the X is $4 together, and which give the probability that 4 choose 2 over 20 choose 2, which give 3/95 probability. And the second outcome is choosing a $2 and a $1, and which is give us $3, and the probability is 4 times 5 over 20 choose 2 is 2/19. And the third outcome is choosing a $2 and a 50-cent, and which give X is $2.50 is 4 times 8 over 20 choose 2 equals to 16/95. And then the fourth outcome is choosing a $2 and a 20 cents. Give us X is $2.20, and the probability is 4 times 3 over 20 choose 2 is 6 over 95. And the fifth outcome is choosing a $1 and a $1, which gives us $2 in total. And then the probability is 5 choose 2 over 20 choose 2 equals to 1 over 19. Then the other outcome is $1. Choosing a $1 and a 50-cent is $1.5. Is 5 times 8 over 20 choose 2 equals to 4 over 19 probability. And this next outcome is choosing a $1 and a 20 cents, which gives us $1.20. And the probability is 5 times 3 over 20 choose 2 equals to 3 over 38. Probability of choosing outcome 50 cent, a 50 cent, and a 50 cent, which gives us $1 in total. 8 choose 2 over 20 choose 2 equals to 14 over 95. And then the last two, we got 50 cent, choosing a 50 cent and a 20 cent is like 70 cents. And then 8 times 3 over 20 choose 2 equals to 12 over 95. And then the last probability that choosing a 20 cent and a 20 cent is 40 cents in total, is 3 choose 2 over 20 choose 2 equals 3 over 190.
Great. Great. So my only consideration is this. So some random variables, you have one possibility, one outcome. Some of them you have two outcomes, right? Like the last two. 20 cents, 20 cents,
Yeah.
that's only one. But 50 cents and 20 cents, you have two. Right? You have two outcomes.
Uh-huh.
Two ways of getting 70 cents. Will that make any difference in the probability?
No, because they're like the same.
So we don't care about right which one is which. We don't care about the first one is 50 cents or the first one is 20 cents.
Mm-hmm.
What are the possible values of x? Okay, because we're focusing on the random variables. Okay, great. I like this way. What was your major? What's your major?
Math major.
Okay, great. Keep doing the good work like this. Yeah, great. Yeah. Yeah, math major really needs like a very, very, what do you call it? Like a serious, consideration. Because when you do proofs, you want to leave no holes to the proofs. All right, great.
Good evening, Professor.
Good evening, Shoyun.
Can you see my screen?
Yes.
Okay, so I'm going to present question number 54 from chapter 3. So the question is, players A, B, C, D are randomly lined up. The first two players in line then play a game. The winner of that game then plays a game with the person who is third in line. The winner of that game then plays a game with the person who is fourth in line. The winner of that last game is considered the winner of the tournament. If A wins each game it plays with probability P, determine the probability that A is the winner of the tournament. So in this question, we have 4 cases. So the case 1 is A is first in line. So the probability of A in the first line, which is 1 over 4. Then if A to be the winner, that means A need to win the second person, then wins the third person and the last person. So the probability of A wins is equal to P times P times P is equal to P to the power 3. So the probability of case 1 is equal to 1 over 4 times P to the power 3. And case 2, A is second in line. So in here, the probability of A is in the second line is 1 over 4. Then if A need to be the winner, that means A need to win the first person, then wins the third person and the last person. So the probability of A wins is equal to P times P times P, which is P to the power 3. So the probability of case 2 is equal to 1 over 4 times P to the power 3. And case 3, A is third in line. So the probability of A in the third line is 1 over 4. Then if A need to be the winners, that means A need to win the second person and the last person. So the probability of A wins is equal to P times P, which is P squared. So the probability of case 3, which is 1 over 4 times P squared. And case 4, A is fourth in line. So the probability of A in the fourth line is 1 over 4. And if A need to be the winner, that means A need to win the third person. So the probability of A wins is equal to P. So, and the probability of case 4, which is 1 over 4 times P. And we need to find the probability that A is the winner of the tournament. So it's all of the 4 cases adding together, which is equal to 1 over 4 times P3 plus P3 plus P squared plus P.
Great. So nice.
Mhm.
You guys do a wonderful job. Great. Thank you, Showing. Anyone has any questions? All right, great. Next one. You see, it seems like life becomes easier, huh, to deal with the independent events.
I'm going next.
Okay.
I'm doing 4.3. So it says 3 fair dice are rolled. Assume that all 6 to the power 3 equal 216 possible outcomes are equally likely. Let x equal the product of 3 of the 3 dice. Find the probabilities attached to the possible values of that x can take on. So I wrote the question. 3 dice are rolled by assuming that each of the 216 outcomes is possible. 6 by 6 by 6. So in the random experiment of rolling 3 dice at a time, there are 6 to the power of 3, 216 potential results. Let x equal the sum of the numerals upturned on all 3 dice. Then the potential values of x can vary from 3, which is for the outcome 1, 1, 1, to 18. 8, that is for the product 6, 6, 6. So 3 dice all turning up 1 with total to 3, and the highest value we can get is 18 if we get 3 6s. Since the 216 products are all equally likely, there's a 1 out of 216 chance to get 3 1s and also 3 6s. And outcomes 3 and 18 have the same probability. So when x equals 3, the probability is 1 over 216.
That's the question, huh? I didn't really get the question.
Sorry.
So the random variable equals the product of 3 dice. Find
Yes.
the probabilities attached to the possible values that x can take on. But your answer is 1 out of 216 is a probability for getting 111 and 666.
Yes.
Well, you have 1, 2. So each die you have 1 up to 6 outcomes
Yes.
considered. Then 6 to 3, 216. I'm not getting this question actually. 3 dice are rolled by assuming that, so this is your solution, right?
Yeah.
Let me read your solution. Either random experiment. No, x is a product of the face value, isn't it? It's a sum. So I read the question is 3 fair dice are rolled. Assume that all 6 raised by 3, because each one has 1 to 6. 216 possible outcomes are equally likely. Let x equal the product of the 3 dice. I mean, probably the face value of the dice, right? 3 dice. Find the probabilities attached to the possible values that x can take on. How many values x can take on?
6.
Only 6?
For one dice. One die.
Well, this thing is 3, right? 3 are rolled.
Yeah.
So you could have
So 3
1.
possible.
So 111 would be 1.
Yeah.
You could have 112.
Yeah.
You could have 113, 114, 115, 116. Then 121, 12, 131, 1. You have, it's more than 6.
Oh, okay.
Right? And then, so this asks you to find the probabilities attached, right? So first you have to find x, the random variable x.
Yes.
Random variable could be 1, could be 2, could be 3, could be up to 6. Then you have 2 times that, right? Then you have 3 times that. Then you have up to 6, because if you get a 166, you get 36. If you get a 666, you get a 216. So
Yes.
so x has many. So the random variable x has many values.
Okay.
All right. And then you have to calculate the probabilities. Well, let's do this. Let's do this. So you have 1, 1, 1. So the first two just 1 up to 6.
Yeah.
Right. So you have 6 already. You have 6 random variable already. I'm trying to list. Anyone else did this question? Then you could have the second one to be 2. So 1, 2, 1, 1, 2. We have to do permutation. So 1, 2, 1, 1, 2, 2, 1, 2, 3. Then 1, 2, 4 up to 6. Then you could have 1, 3, 1 up to 6. You see how many? This is up to 6. 1, 3, 1, 6, 1 up to 1, 6, 1. Because you could make a 3 dimensions list.
Yeah.
Then the first one can be, so you do have 216 possible outcomes. Yeah. But how many? So you have to, but the x take on the products, they're same values, right? Only one, so only one, so only one of 216 but the middle ones can be the same. So we have, so 1, 2, 1, 1, 1, 2, and 2, 1, 1 are the same. So we
Yeah.
could have 1, 2, 3, up to 6, then 2 multiplied by this number, right? But 2 will be same, 2, 2, 4, 2, 4, 6, so on and so forth. I don't know how many. So anyone did this question? So this is a 4.3. All right, this one would be good to do it. All right. So everybody try this one. I may put this one on the exam. Okay, Anjuli, thank you anyway.
All right.
Okay. Next one. For the next one will be 6. Because it will be multiples of 2. So I'm interested in doing Anjuli's question 4.3. I would encourage everybody to do this 4.3. All right, maybe you can present next class. Who's the next one? So multiples of 2, multiples of 3, the multiples of 4, and the multiples of 5, multiples of 6. All right, who's next one? What's going on? Jay, Catherine, Tom, Yinping. So,
Okay, I can be next.
okay.
Can you see my screen?
Yeah.
My question is 4.5 and 4.6. 4.5 is that X represent the difference between the number of heads and the number of tails obtained when a coin is tossed n times. What are the possible values of X? Let m be the numbers of tails, so the number of heads is equal n minus m. So X is equal h minus m, so it's n minus m is equal n minus 2m. And for 4.6, in problem 4.5, for n equals 3, if the coin is assumed fair, what are the probabilities associated with the value that x can take on? For the first one, we have 3 heads and 0 tails. The x will be 3, so the probability is 1 over 8. And when the heads have 2, tails have 1, the x is equal 1. The probability is 3 over 8. When the heads is 0, tails is 3, the x is equal minus 3. The probability is 1 over 8. The heads is 1, the tails is 2, and the x is equal minus 1. The probability is 3 over 8. So add all of them is equal 1. And that's it.
Okay, great. So we are in the chapter of talking about random variables. So this is different from talking about probabilities before. Before, probability of an event, right? There's no variables considered. So one event is just one event. So probability of that particular event. But now, why we're using random variables? Because the different values and we can represent with this variable. So this variable, you know, can be assigned with different values. Just like this one just showed, right? The difference between two. So it could be different numbers. All right, anyway, we're getting there. We're getting to understand random variables. Okay, so who's next? Yongxin, you have presented already, right?
Yeah, I was first.
Yes. Okay. Next one.
Can you guys see my screen?
Yeah, Catherine.
Okay. Do you see the
Go
question,
slow.
3.7?
3.7. Yes. Go
Can I do
slow, okay?
3.7 and 3.8?
Sure.
Okay. So 3.7 is the king comes from a family of 2 children. What is the possibility that the other children is his sister? So his family has 2 kids, and the only possible birth orders for 2 kids is boy, 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 girl, and girl, girl. However, we know that it can't be girl, girl because the king is
I
not a
think,
girl.
hold on a second, Catherine. I think this one is presented before.
Oh,
Yeah, I remember that. I remember this one has been presented by someone.
okay. What's 8? 8 is similar. I can move to that.
3.8. Okay, 3.8.
So it's the similar concept of the second child. So we still have that
I
order.
don't. Can you focus to 3.8? Your screen. I don't see it on the
Hold
shared screen. I still see 3.7.
on. Okay. I don't. Okay. I see. Sorry. Yeah. I shared the wrong one. Here we go. I can make it bigger.
Okay, thank you. Got
There we
it.
go.
I see it. 3.8.
So
Yes.
the question is: a couple has 2 children. What is the possibility that both are girls if the older one is a girl? So the possible birth orders are boy, boy, girl, boy, boy, girl, and girl, girl. So the possibility of both are girls is 1 out of 4, which is girl, girl from this list. It's the only one that has 2 girls. So the possibility of a bigger child to be a girl is 2 out of 4 because you have a girl boy combination and a girl girl combination. So the possibility of both are girls is 2/4 divided by a half, which gives you the possibility of a half as seen before.
Hold on. Both are girls is 1/4, isn't it? 1 out of 4.
Yes, I'm sorry, that was a typo. 1 out of 4.
Yeah.
Sorry.
You don't need to do this division. 2/4 divided by half. This is 1 out of 4. Right? There's no.
Yeah.
What's 2/4 divided by half? You don't need this step. Just 1 out of 4. Because you
Okay.
have 4 outcomes. This is just one of it.
Okay.
Okay. Oh, then what is it? So you have to find the conditional probability. You haven't finished yet, Catherine. Catherine, can you hear me? Let's finish it.
Yeah, it said, what is the possibility that both are girls if the older one is a girl?
Yeah. Oh, that's why you have the debate. Okay. Can you put it back on? Now I understand why you have that. Can you put it back on? I don't see it. Can you share your
Oh, I'm
screen
sorry. I
again?
stopped sharing. I could reshare it. Give me 1 second.
Okay. Okay, now I understand why you have 2/4 divided by half. 2 out of 4.
Sorry.
Because the older one to be girl. Okay.
So I'm trying to find it. There we go. So both girls is 1/4, and the older one to be a girl is 2 out of 4.
That's
and
right.
then it said what's the possibility that both are girls if the older one is a girl. So that's where the 2/4 comes in, because the older child being a girl is 2/4, and then out of the girls it's a half.
That's right. So both are girls. So okay. So this notation confused me, because you have a conditional probability. You have to use a conditional. If you don't want to use a notation, you have to use words. So can you scroll up to see the question? The question is, if both are girls given if the older one, right? So given the older one is a girl, what's the probability of both of them are girls? So you need to
Yeah,
put
with
this
the
one
older one being a
into a
girl.
probability, right? Because you have to remember the conditional probability, right? So both are girls given the older one is a girl. So now I understand why you have the division. All right. Okay. Thank you, Catherine. All right. Anyone's left? Jie, did you present it already? Or Tom? Tom hasn't, right? Jie did already. Tom hasn't done yet. I think Tom is, yeah, Jie did, yes. Tom, are you here? I think we're left with Tom.
Professor, I would
Oh,
like
your question done already? Okay, so next time then. Oh,
Professor, can I do
yes.
4.14?
Sure. Let me make you a presenter. How do I call your name? Which one you prefer to be called?
You can call me Sumit.
Sumit.
Yes.
Okay, Sumit. Nice.
Share application. Okay, can you see?
Yeah.
Okay, so the question is, on average, 5.2 hurricanes hit a certain region in a year. What is the probability that there will be 3 or more hurricanes hitting this year? So for this, we need to use the Poisson distribution formula to solve this. This is the Poisson distribution formula. Here, small x is the random variable, which is the number of hurricanes in a year.
Did we talk about Poisson distribution formula? Did we? I forgot.
I did not attend last class. I'm sorry.
We haven't talked about the Poisson.
Oh. I
but
mean,
this
then
is 414.
I can just show the.
Okay, go ahead.
Yes. So this is the.
Can you
just a formula plugin. Yeah.
Can you tell us how do you know to use the Poisson distribution formula? Because everyone can learn from this. Because I haven't talked about yet.
Yes, because we have the 3 things that we need. We have the random variable, and we have the mean. So, and the x is the number of hurricanes we're interested. So when we have these 3 items, we can use the Poisson distribution formula to solve a problem. So in this instance, the small x is the random variable, which is we need to go from, because it says the 3 or fewer hurricanes hitting this year. So we need to include 3 and everything below 3 as well. And lambda is the mean number, which is also already given to us by on average. Average means mean 5.2 hurricanes hit a certain region. And x, the big X, is the number of hurricanes we're interested in that is going to hit this year. So
I don't see big X, small x. You have a small x?
So the small x is p of x in the formula. This is the small x, and that is the big X. Does that?
What about the denominator?
Yeah, I should have written this handout. I just took a picture. So this is how the picture came out, basically. So this is the small x. This is the small x, and that one is the. Wait, this is. I need a better picture, but I have the solution here, handwritten. So going from x less than equal to 3, x equal to 0, x equal to 1, x equal to, so we just have to add all the probabilities from 0 to 3. In this instance, we're going e to the negative 5.2, which is the lambda, and the 5.2 is the lambda in this instance. X is the
I think the x is the same. You see, your first x is the random. Hold on. Can you go down a little bit?
Yes.
Your notation. So x is random variable representing the number of hurricanes in a year, which is 0 to 3. Then the bottom x is the number of hurricanes we're interested in.
Yes.
Okay,
Actually,
I
yes,
see.
you're right. You're right. So they are the same notation. I was just trying to distinguish between x right here on the left-hand side and these
I
x's that
see.
we formula.
This should be this.
But
Okay.
it,
Yeah.
so it's just simply plugging in the values into the formula itself. So e to the power negative
0,
5,
1, 2, 3. I see.
0, 3, and the final answer is 2381.
The final answer is about 24%.
Yes, 24% of hurricanes. Yes.
Okay. All right. Okay, we learned. Thank you.
Sure.
Let me find you on the list so I can give you credits for this. Okay. All right. So I think we're done with the presentation, right? If anyone else like to present, let me know. So far, just to know the random variables. So today, my plans talk about expected values, right? So which, as I mentioned yesterday, the day before yesterday, so it's a very important concept of probability theory, and we use it to predict many things about expectation of a random variable. So if x is discrete random variable, discrete again countable variable having a probability of mass function, all right, probability of x, right? Then the expectation or expected value of x denoted as this. Okay, we just use this notation because notation is just convention, right? So we don't have to write a lot of words. We can save a lot of time by using notation because it's a convention. You know, everybody knows its meaning. So expected value we represent with the e with this bracket of random variable x. And is the sum of all those x, right? X is random variable value times its probability, then adds up all of them. Okay. Okay, in words, the expected value of x is a weighted average of the possible values that x can take on. Right? Each value being weighted by the probability that x assumes it. For instance, on the one hand, if the probability mass function of x is given by this, so probability of getting 0 is a half, and the probability of 1, same as the probability of getting 1, then the expected value is 0, the random variable, the value of the random variable multiplied by its probability, plus 1 times its probability, which in the end equals to half. So expected value is half. So this is just an ordinary average of the two possible values, 0 and 1. Then that x can assume. On the other hand, if probability of getting 0 is 1/3, probability of 1 getting 1 is 2/3. If we do this, expected value is 2/3. So this is a weighted average of two possible values with 0 and 1, but the different weights. Right? For the first one, getting 0 and getting 1 have the same weights, 50% chance. But here, 0 is 1/3, 1 is 2/3. So where the value 1 is given twice as much weight as the value 0. So the probability of 1 equals 2 times the probability of 0. Another motivation of the definition of expectation or expected value is provided by the frequency interpretation of probabilities. This interpretation partially justified by the strong law of large numbers. We will talk about the law of large numbers in the end, but for statistics to be a science, right, it stands up on two things, on two legs. One of the legs is the law of large numbers, and assumes that if an infinite sequence of independent replications of an experiment is performed, then for any given E, the proportion of time that E occurs will be probability of E. Now consider random variable x that must take on one of the values x1 up to xn with respective probabilities p of x1 up to p probability of xn. I think of x as representing our winnings in a single game of chance. Okay. Yeah, if you want to play game with your friends, you set up certain rules. You can always calculate, you know, your chance of winning the expected value. That is with a probability of a p of probability of xi, we shall win xi units for I from 1 up to n. By the frequency interpretation, if we play this game continually, then the proportion of time that we win xi will be probability of xi. Since this is true for all i's up from 1 to n, it follows that our average winning per game will be expected value, okay, which is from 1 up to n, is those xi's multiplied by its probability, then adds up all of them. Let's see the example 3a. So we want to find expected value for this random variable, which is the outcome when we roll a fair die. All right. So probability in getting each, because it's a fair, so which means getting probabilities for every number from 1 to 6, just 1 out of 6, because it's a fair. So we obtain expected value with 1 times its probability, 2 times the probability, 3 up to 6 times 1 of 6, which is a 7 over 2. Pretty simple, huh? So next example, we see that I is an indicator variable for the event A if I have 2 values. 1 if event A occurs, 0 if the complement occurs. The complement of A occurs. So we want to find expected value of this such I. So that means probability of 1 equals probability of A, right? Because A occurs. Probability of 0 equals the probability of the complement of A. So probability of 1 equals probability of A. Probability of 0 equals the complement, the probability of the complement of A, which is 1 minus probability of A. So then, because 0 times anything will be 0. So this part will be gone. So we only have 1 times probability of A, which is just probability of A. So words, the expected value of the indicator variable for the event A is equal to the probability that A occurs. Makes sense, right? If anyone has any question, feel free to stop me at any time. Let's see this example. A contestant on a quiz show is presented with 2 questions, question 1 and 2, which he is to attempt to answer in some order he chooses. If he decides to try question I first, then he will be allowed to go on to question J, and J cannot be equal to I, only if his answer to question I is correct. If his initial answer is incorrect, he is not allowed to answer the other question. Okay, so he has to be right until I. If his initial, the contestant is to receive VI dollars if he answers question I correctly. I equals 1 and 2. For instance, he will receive V1 plus V2 dollars if he answers both questions correctly. If the probability that he knows the answer to question I is the probability of I, which question should he attempt to answer first so as to maximize his chance of winning? Assume that events EI, so E1, E2, that he knows the answer to question I are independent events. So on the first hand, if he attempts to answer question 1 first, then he will win nothing with probability of 1 minus P1. But Once V1 with a probability of P1 multiplied by 1 minus P2. Because this is given probability, he knows the answer to question I is this, right? It's P1, P2. Then he gets V1 plus V2 with a probability of P1 and P2. Hence, his expected winning in this case will be V1 times P1 times 1 minus P2, right? Because again, 0 times anything, we just can ignore this. V1 times this, then plus V1 plus V2 times this. On the other hand, if he attempts to answer question 2 first, his expected winning will be V2 times this, right? Because we could just list this to be V2, then with probability of P2 times 1 minus P1. And so this one, V2 times P2 times 1 minus P1. Then the second one will be the same, right? If he wants V1 plus V2, that's multiplied by P1 plus P2. So it's better to try question 1 first, if this one is greater than this one. Because this part is the same, right? This one and this part is the same. So you just have to compare this one and with this one. So if so it's better to try question 1 first if this has a better winning chance than this, right? Or the other way around, or we just rearrange this, so get this V1 P1 divided by 1 minus P1. Oh, this is a nicer one, right? This is all with the V1 and P1s. This is all with the V2 and P2s. Let's see the example. If he is 60% certain of answering question 1, right, was $200. So V1 is 200 and P1 is 60%. Correctly, and he's 80% certain of answering question 2. So probability, so P2 equals 80% and V2 equals 100. Then we can compare it. We can plug into this, right, to calculate to see which one is bigger. Then he should attempt to answer question 2 first, right, to do the calculation. So because this side he gets 400, expected value is 400, not expected value because we didn't calculate the second part. We just ignore. We're comparing these two, two ways of doing things because this part are the same. We just ignore it. We just compare partially of the expected value. So do the first question 400. 400. Do the second one is 300. So of course, choose the first one in this case. Anyone has any questions? Again, doing probability questions, you really have to list the stuff, all right? You really have to list the stuff. You don't jump in to do the question. You have to try to use the notations, right? You have to make a list. Couple of you are really good at this. Draw pictures, list all those notations, stuff like that. Then apply the formula. Probability has a lot of formulas. Apply the proper formulas. It's right. Catherine is saying it makes it easy to understand. Not only that, Catherine, you are math majored. It just forms, it just how do we say it? It looks like it makes, right. You could say it makes it easier to understand, but the truth behind it is you're training your brain You're training your brain to work logically and precisely. Let's put that way. Especially for your math major, you really have to be precise. And this, to me, this is the only way to make it precise. You see, when people take exams, many people make mistakes. Why? Because the thinking of the brain is not precise. By doing so, you're training your brain to be precise. Anyway, all right, let's see this example. A school class of 120 students is driven in 3 buses to a symphonic performance. There are 36 students in one of the buses, 40 in another. Okay, 40 in another, and 44 in the third bus. So when the buses arrive, one of the 120 students is randomly chosen. Let X denote the number of students on the bus of the randomly chosen student, and find expected value of this particular randomly chosen student. Okay, solution. Since a randomly chosen student is equally likely to be any of the 120 students, it follows that probability of random variable equals 36, right? The first bus is 36 out of 120. So the probability comes from the first bus is that it could be any one of these 36. So it's 36 out of 120. Probability come out from the second bus, 40 in the second bus, 40 out of 120. Probability getting off from the third bus, 44 over 120. So the expected value is the random variable, the value of the random variable multiplied by its probability. This is a simplification of this. Right? 36 over 120. The simplest form is 3 out of 10. Then plus 40 times 1/3, 40 divided by 120, 1/3. 44 multiplied by, simplify this, divided by 4, 11 over 30. So it's about 40 something expected value. So what does this say? So however the average number of the student on the bus is 120 divided by 3 is 40. So this shows that expected number of students on the bus of a randomly chosen student is larger than the average number of students on the bus. So this is a general phenomenon, and it occurs because the more students there are on the bus, the more likely it is that a randomly chosen student would have been on that bus. As a result, buses with many students are given more weight than those with fewer students. Okay, this just show one of these phenomena of calculating expected values. Remark. Okay, you read the remark. We're talking about the center of gravity. Let's see how much of this 4.4. Okay, let's talk a little bit about this 4.4. Expectation of a function of a random variable. Suppose that we're given discrete random variable along with, okay, so later on we're going to talk about discrete versus continuous. Okay, so we have 2 kinds of random variables. So right now we're dealing with a discrete. So X can be assigned to one specific value. And later on we're talking about continuous random variable. We're given discrete random variable along with its probability mass function, right? The probability of X. And that we want to compute the expected value of some function of X, say g of X. How can we accomplish this? One way is as follows. Since g of X is itself a discrete random variable, it has a probability mass function, which can be determined from the probability mass function of the random variable. Once we have determined the probability mass function of g of X, we can compute expected value of such g of x by using the definition of expected value. Well, let's see an example. So the random variable x takes on any of the value -1, 0, and 1. So with respect to the probability, getting -1 is 20%, getting 0, 50%, getting 1, 30%. So calculate expect x squared, x2. What does this mean? Compute expected value of x times x squared. Let's see. Okay, let y be x squared. Then the probability mass function of y is given by okay, y is 1, x squared is 1, equals the probability of x equals to -1, random variable to -1, and x is 1. I'm sorry, I don't get this notation. Different textbooks use a different notation. What could this be? Yeah, is saying x equals -1 and x equals 1, x squared equals 1. I was thinking that might be that, but will that make sense? X squared, because right, -1 would be -1 squared would be 1, 1 squared would be 1. So then why this is a plus? Oh, okay. Because this the random variable could be -1, random variable could be 1, so x squared is the same to be 1. Okay, that makes sense. Yes, I think you are right. First two x values are only one value. Yeah, I think you are right. Yes, thank you. Thank you. Yeah, so add those two together. That's 0.2 plus 0.3, which is 0.5. Then probability of getting the rest of it, because getting 1 or 0, x squared either 1 or 0, right? Because 0 squared is 0. All right, so which is 0.5. Now we can calculate the expected value of this x squared, which is 1 times 0.5, right? Because no more next one, all right? So the original random variable represents the -1, 0, and 1. Since now we're putting random square variable square, -1 square is 1, 1 square is 1. So we only have 1 times 0.5 plus 0 times 0.5, which equals 0.5. It's the same as, so know that 0.5 is expected value of x squared. It does not equal to expected value of x squared. Expected value x squared is 0.01. Why? Oh, because this is gone, right? 0 times 0.5 is 0. Then we have expected value of -1 times 0.2 plus 1 times 0.3. That would be 0.1. Then 0.1 squared would be 0.01. All right, so now I think I understand that's notation. Anyone has any questions? Okay. Let's read this. Although the preceding procedure will always enable us to compute the expected value of any function of x from our knowledge of the probability mass function of x, there is another way of thinking about probability, expected value of g of x, since g of x will equal the g of G of a specific, so this little x represents a value of this random variable. So the capital letter X represents a random variable, and the G of little x represents a specific value is equal to X. It seems reasonable that E of G of the random variable should just be a weighted average of the values of G of X, with G of X being weighted by the probability of X is equal to X. That is, the following result is quite intuitive. Okay, proposition. If X is a discrete random variable that takes on one of the values xi, I greater than or equal to 1. So in this case, this discrete random variable takes infinite many values with respective probability of P of xi. Then for any real value function g, expected value of this function g takes the random variable as input equals to g, so the function value evaluated at those xi's multiplied by probability of the xi's. Makes sense, right? So before proving this proposition, let us check that it is in accord with the results of example 4a. Applying it to the example yields expectation of x squared. Why use wiggly? Now you see these wiggly parentheses, which is -1 squared times 0.2, 0 squared times 0.5, or 1 squared times 0.3, which we get 0.5. Right, this is the expected value of x squared, which is agreement with the result given in 4a. Okay, I'm going to skip the proof. All right, you can read the proof yourself. Just dealing with this summation signs. Let's see one more example. A product that's sold seasonally yields a net profit of $B for each unit sold, and a net loss of L for each unit left unsold when the season ends. So the number of units of the product that are ordered at a specific department store during any season is a random variable having probability mass function of a probability of I, and I is non-negative starting from 1. If the store, starting from 0. If the store must stock this product in advance, determine the number of units the store should stock so as to maximize its expected profit. All right, so let X denote the number of units ordered. So our goal is to determine the number of units the store should stock and to maximize its expected profit. Okay, its expected value. So let X denote the number of units ordered. If S units are stocked, so S represents units stocked, then the profit, call it probability of S. Then the profit, call it P of S. So this is a function. This is a function. Can be expressed as B times the random variable. Remember the $B is sold, right? If 1 is sold, so get $B. So B times X many being sold minus unsold. So how many unsold? The number in stock minus sold multiplied by L. S is, if unsold at the end of the season, the store will lose L for each. How many unsold, which is how many stocked, subtract the sold. And if we do this, what do we get? This equals SB, really? So let's see. So this is BX minus S times L. minus, oh yes, you see this is minus XL. That becomes plus XL. So B plus L, that's S, right? Oh no, not B plus L. So hold on a second. Where did this get SB? S times B. Okay, so this is the minus S, then plus XL. Plus XL. So what is BX plus LX? Then minus S. That's S times B. That's S times B. Oh, okay. So this is two functions. My goodness. Okay, domain of the first one is if the random variable is less than or equal to S, right? Of course, because we have unsolved. But if everything is solved, so random variable greater than S, right? That just equals to S times B, of course. You know, how many mean everything is solved. So how many stacked? S many, and sold, each one sold for B dollars, so that's SB. Yes, that makes sense. I think someone is trying to explain. Piecewise function, yes. Piecewise function. Okay, so if everything is sold, we have the second one. If we do have one unsold, we have first one, hence expected profit equals to BI, so we sum up all this. BI, right, the X value for I, subtract X minus I times L, multiplied by each one's probability. Then plus, because we have two parts, we have either this way or this way, so expected value. We add up all those possibilities for this. We add up all the possibility for this, which is SB times probability of I. And I goes from S plus 1 to infinity. So this is the oversold, right? So the stack, so this part is we have unsold. These ones, so I starts from S plus 1. Remember, S is the number of atoms being stacked. So if we do this, we do the calculation. Let's see how does this calculation. So factor out B plus L because this has a negative IL becomes BI plus IL. So have this. Then we'll have I multiplied by probability of the specific one. And this minus S, right? Minus S times L. So separate with the minus SL. Then, because this has nothing to do with, so SL has nothing to do with this index I. So we can put outside the summation sign. Just adds up all the probabilities of this. Then this one, SB can be factored out. SB can be factored out outside the summation sign. And since this I starts from X plus 1, right? So the store stacked S many, now S plus 1. So not in the ones not in the stack being sold. So S plus 1, so this can be rewritten as, so factor out XB outside the summation sign, do 1 minus, right, these ones, because for I goes from 0 to S. Yeah, the first S many ones, the stacked ones. Keep doing the calculation. Let's see. Now I because we have this SB, Now we have this one, we have this one, right? So that means that's because this has SB, this has SL, so that's SB plus SL, then multiplied by the sum of these probabilities. Okay, in the end, we still get these notations. And if we give some numbers, do we get some numbers, some examples? Not really. Okay, let's see this. To determine the optimum values of S, right? That's our goal, right? We want to figure out what's the best number for S. Let us investigate what happens to the perfect, because S appears here, S appears here. Happens to a perfect when we increase S by 1 unit. By substitution, we see that expected profit in this case is given by, so we want to change S to be X plus 1. Now we change every S to be X plus 1 to see what happens. And when we simplify, so we get this. We get this compared to this, I guess. So stacking S plus 1 units will be better than stacking S units whenever this happens. So this is from comparing. So, right, if we do this, expected value of S plus 1 many, subtract expected value of S many, will be this one, or B minus B, B minus this. So what we could do is B over, so if this one is less than B over B plus L, yes, right? Because this is subtraction. This is subtraction. Yeah. If this one is less than B over B plus L, means this whole thing is less than B. Right? This whole thing is less than B. Then this will be a positive number, which means it's better to stack one more unit. All right, let's see this. Because the left-hand side of equation 4.1 is increasing S, while the right-hand side is constant. Right, this is constant. The inequality will be satisfied for all values of S less than or equal to S star, where S star is the largest value of S satisfying equation 4.1. Okay, interesting. Okay, it follows that stacking S star plus 1 atom will lead to maximum expected value. Very dry, huh? Because no numbers to work on. Corollary, if A and B are constants, then expected value of A times the random variable plus B equals to, we can factor out A equals to A times expected value of the random variable plus B. Right? So which means A and B, because A and B are constant, it doesn't really participate into the calculation of expected value of the random variable. Okay, that's all what it means here. And we can prove this by, let's see. So by the definition, right, we prove by the definition. Then we have AX times the probability of X, and this A is constant, has nothing to do with X, so we can factor out. And this B also has nothing to do with the random variable value, we can factor out. And rewrite this, right? It's just A expected, so this part is just by definition of the expected value. So this is a Q proof. The expected value of a random variable X, expected value X, is also referred to as the mean or the first moment of X. Okay, this is just a term. Either we call mean or first moment of the random variable. The quantity of expected value of the random variable raised by n we did a square n equal to 2. For n greater than or equal to 1 is called the nth moment of x. All right. I forgot about this. Now I remembered. So x raised by 1 is called the first moment of the random variable. And x raised by n is called the nth moment of x. Okay. So by proposition 4.1, we can have expected value of x raised by n equals to this summation of this, the value of the random variable raised by n, which we did this, right? They should talk about this before the example of expectation of x squared, because I totally forgot about this, right? So I would put this before the example. Okay, anyway, so I'm going to talk after here. Anyone has any questions? Okay, some of you are doing very, very nicely, and some of you hasn't presented much yet. I don't really know where you are. And hopefully those ones, let me show you this. Let me show you, maybe this could be an encouragement or discouragement. Let's see. Okay, let's take a look of this presentation. Well, 4 times, 2 times, 0 times. By the way, I don't think I ever seen this student. I sent the emails out. I didn't get any response. Crystal, 0, Chanel. I think Chanel is in class. I see Chanel here, right? Chanel? Yeah, you are here. Would you please prepare yourself to present? Because presenting is help all of us to review the material I have talked about, and also to, to help me to understand your position in this class. You know, how much you understand me, how much I'm confusing you. Okay, please. And also, Ice, right? You haven't presented anything yet. And then 5 times. Ryuan, no time yet. Darius, twice. This person is not here anymore. 5 times, 5 times, 8 times, 9 times. Keep going. Okay, you'll get extra credit for this. 6 times, 3 times. 7 times, 6 times, 4 times, 3 times, 4 times. Jaden, not yet. 7 times. Please. All right. Jaden, you are here. So would you please review when you are here? Chanel, Ice, please prepare yourself to present. Okay. You don't have to pick a difficult one. Pick something you think you really understand. Thank you, guys. Thank you. All right. You guys doing marvelously. And for those ones you like to present, all right, you are teaching me, okay? Because I haven't done any of this homework yet. So I really appreciate it. Okay, thank you guys. Keep up your good work. All right, so that's all for today. I'm going to stop recording. And if